Okay, so let's continue our discussions, and in today's lecture we'll look at one important application of diodes, which is for converting a AC signal, AC voltage that we get in our power sockets, and converting them into a DC voltage of appropriate value for a variety of applications. All right, so as just mentioned, so the idea is that the input is an AC signal from the that we get in our homes, and that's 220 volt RMS, and the peak value is then 311 220 volts multiplied by square root to 311.127 here, and the frequency is 50 hertz. And let's say for some application we would require let's say a voltage of 12 volts. Well, for some other application it could be 5 volts or 6 volts depending on what we have connected over here. So a load resistor is connected here, and so what we are looking for is input is a sinusoid, and then we are looking for a DC, a voltage which is constant with respect to time here. So that's what we are looking for. And so our first strategy for doing that is as follows: that we are given this AC signal here, and what we are going to do is a half wave rectification, meaning that we will cut off the negative part here, since we want a positive plus 12 volt. So we'll cut off this negative part here, and that's called the half wave rectification. And then what we'll do is, since we want a DC, and you see that this is a periodic signal, so it has a number of frequency components, and we are interested in DC. So what we need is a filter which will filter out all the frequency components, leaving behind a DC for us, right? So we'll see that how we do that, and so basically a low pass kind of a filter, and so we'll then be able to obtain our desired DC voltage here. So the first step is half wave rectification. We'll see later on that we may do full wave rectification as well, and so we start off with half wave rectification, where the output is same as the input in the positive cycle, and in the negative cycle it rejects it altogether, and then the filtering action here. Okay. All right, so our diagram for the power supply then becomes a half wave rectifier circuit and a filter circuit, and then of course there is the load resistor here. All right, so half wave rectifier circuit is very simple. It's simply a diode, one single diode that you see here, and if we apply our sinusoidal signal with a peak value of 311, and so this is what we'll obtain. In the green is the sinusoid input, and the output will be basically in the positive cycle. We can see positive cycle, our diode will be, note that the value is 311.127 here, so very high. The diode drop may be 0.7, 0.8 or so. So as a simple model, we have neglected that, assumed diode to be like a short here. And so in the positive cycle, this is how the circuit is, and that's why V0 is almost equal to Vs, which is what we see here. There is a drop across the diode, but we are not able to see it because it's small compared to the value of the voltage that we have here. And in the negative cycle, the diode is reverse biased, and therefore it's an open circuit. Of course, we are assuming that the breakdown voltage of the diode is much higher than the peak value of the voltage that you see here. And so what we get is this value here. I mean, this is an open circuit here, and therefore there is no current, and V0 is equal to 0 here. So in red we see 0 here. So that's half wave rectification. But note that we get a value, even if we filter it, let's say we connect a filter, the output that we will get will be close to the peak value here, which is very large for most of the applications, portable applications for which we require DC charging. The value of the output voltage may be 5 volt or 6 volt or 12 volt. So this is very large here. So what it says is that we cannot take directly the input voltage that comes in the power outlet and directly half wave rectifier and filter it to obtain the value that we want, and because that value would be very high. And so what we need is we must reduce the input voltage, and that's where a common way of doing that is through a transformer. And so we have a transformer, we have a step down transformer here, and we know that Vs by Vin that will be given by the turns ratio here, N1 by N2, and therefore depending on the application, for example, let's say for V0 to be 12 volt, the input required, note that if we look at this part of the circuit, this is nothing but shown over here, and Vin is the output, Vin is the voltage across the secondary here, and therefore if you want V0 to be 12 volt here, then you require a peak value of 12.7 here. So 12.7 here, and the input is of course 311.127, we've seen that here, and therefore the turns ratio N1 by N2 is 24.5. And so if we use a transformer with this kind of a turns ratio, then we'll be able to get here 12.7, and here we'll get 12 here. So let's see if that happens here. So we've connected a transformer, and if we simulate this particular circuit, then this is what we obtain. Note that the output is very close to the output is in red, very close to 12 volt here, and so the input is about 12.7. You can see here the output is close to 12. You can see it here, 12.088 here. Okay. All right, so that's a zoomed view of the signals, and so with the transformer we are able to get the output of the right magnitude, and with half wave rectification we can get this kind of a graph. So the next thing that we have to do is add a filter. So in this case the filter that we will look at is a very simple filter where we connect a capacitor. And so the idea is that all the frequency components, they will get, if we choose the capacitor to be large enough, they'll get shorted here. And for DC, the capacitor is an open circuit, and therefore the DC voltage will remain, and all the frequency components will get shorted. And so let's see. So this is what happens here. So we connect a capacitor. This is in red is what is shown over here. So the capacitor, in the positive cycle, we've said the diode turns on, and V0 follows the input, and reaches close to the peak value with the difference of the diode voltage here. And once the input starts falling, the capacitor maintains its voltage here. And therefore the diode will become reverse biased. And the capacitor voltages will start to discharge through RL, but if we choose the capacitor properly, the discharge is very small, and therefore you get almost like a constant voltage here. And whatever is the amount of charge which has been lost through RL, when the next positive cycle comes in, the diode momentarily turns on again and restores the capacitance value to the value of 12 volt or so, for which we have designed the circuit here. And this process repeats. So this is shown over here. And so in this part, note that diode is forward biased, and the moment the input shown in green starts to fall, and you need at least 0.7 volt or so to have adequate conduction in the diode, and therefore beyond this particular point here, once the input starts falling here, input starts to decrease, there's not enough voltage here in the diode, and therefore in this particular part here the diode is reverse biased here. The diode is reverse biased, and here is the diode is forward biased. And then again in this small part here the diode gets forward biased again. Once the input voltage goes above the output voltage here, the diode becomes forward biased, again starts conducting. in this part, most of the time that you can see here, the diode is reverse biased. The diode is reverse biased and there is no path here, and the capacitor is basically discharging through RL here, and that's why there's a slight decrease in the voltage that you see here. All right, so let's draw the output in more detail here. So this is how initially the diode turns on and the output charges here, and then we just saw that the output capacitor is discharging, so it goes like this here, and then the diode turns again and restores the capacitor charge, and then again the capacitor discharges, and it goes like this here. So what we note is that we wanted an output which is a DC, but the output is has a ripple. We call this the decreasing and then rising and decreasing and all that. We call this a ripple here. And the magnitude of the ripple, if we see that this is the VM max, the maximum value, and the VL is the lowest point of the output voltage here. So we can define ripple voltage as VR as VM minus VL, the total variation in the output voltage here. Note that we neglect the initial part here. So we look at steady state. So VM minus VL is the ripple that is there here. And the ripple in this case for this particular example is output is 12, VM is 12.070 and VL is 10.098. So V ripple is 1.997 volt here. The average output voltage is, one could define it as VM minus VR by 2. VR is the total drop from here to here, and the average value would be somewhere in the middle here, and so that's why VM minus VR by 2. And in most of the designs, the ripple is very small, and so the average output voltage is very close to the maximum value VM here. All right, so the ripple is something that is something that we don't really want, and the ripple frequency is at the input frequency that you see here, and this DC voltage is going to power lots of devices, and this ripple here can get into the circuit and cause unwanted and can get amplified also. For example, if this DC voltage is used to power an amplifier, the ripple can get into the amplifier and can get amplified also, and therefore one would have an unwanted frequency component, and that is something that is can be a big nuisance and something that we really don't want. So what does the ripple really depend on? The magnitude of the ripple. So let's look at this particular circuit here, and we note that in this particular part of the waveform here, which is causing a ripple here with this part of the waveform, the diode is reverse biased, and effectively the capacitance is discharging through RL. And so if we look at this the equation here, if we just do a KVL at this particular point, so C nodal here, C dV naught by dt plus V naught by RL equal to 0, or dV naught by dt is equal to minus V naught by RLC. And therefore the equation is very simple. V naught is Vm. We have seen earlier RC circuits, Vm multiplied by e to the power minus t RLC here. So that's how the capacitor is discharging. The capacitor is discharging through RL here. All right, so how much is the ripple? Ripple is Vm minus VL, so that we can calculate easily. So it starts from, if we call this t equal to 0. So as capacitor keeps on discharging till a point where the capacitor voltage falls below the input voltage here. And then the diode turns on, and the diode will charge up the capacitor again to a value close to the peak of that particular voltage, minus of course the diode drop here. And so VL will be equal to Vm e to the power minus T1 by RLC. And now what we can do is we can make some using the definition of ripple voltage Vm minus VL. So we can write it VR equal to Vm 1 minus e to the power minus T1 by RLC. And because normally the design is done in such a way that the time constant RLC is very, very large compared to this time period here, because we don't want the capacitor to discharge in a significant manner here. And so this condition is most of the time true, which allows us to basically expand the exponential here. So the exponential we can write, so if T1 is much smaller than RLC, so we can take the Taylor series expansion of exponential, and we can write VR is close to Vm T1 by RLC. Okay, so that makes the expression of VR simple. The next thing is, what is the magnitude of T1? And so again, if we look at a good design, what we would find is that the capacitor charges up to the maximum and then discharges here. And then the discharge is very little. So this value is very close to the peak again, and very close to the peak again. And therefore, the separation, the period from 0 to T1 is almost equal to the time period that you see here. So that's the next approximation that we'll make, that instead of doing a very accurate calculation for T1, we'll assume that T1 is very close to T here, right? So T1 is almost equal to T, and therefore VR ripple, which we had calculated Vm T1 by RLC, so we will substitute instead of T1 the time period T here, and we know that 1 over time period is frequency, so we can obtain this particular expression for the ripple voltage here. So V ripple equal to the maximum value here, Vm, divided by the frequency of the input sinusoid, and the time constant RLC here. Okay, so there are approximations in this. We can see that we are making an approximation of the T1 is practically equal to T, and also we had assumed that we had taken an exponential and approximated by a Taylor series expansion, keeping only the first term. So there are approximations here. And so the value that we will get will not will have some amount of error associated with it. So let's look into it. So this is the design that we have here. So a transformer here with 100 microfarad, 1K load resistor here, and these are the results obtained from simulation. And therefore one can see a ripple of 12.070 minus 10.098, so about 1.97. So let's say about 2 volt here. And if we use our expression, VR equal to Vm, F RLC here, and if we plug in our expression 50 Hertz, RL of 1K, and capacitor of 100 microfarad, we get 2.4 volt here. So we have a little bit of error because note that the value is not exactly as we discussed, there's a little bit of error involved here, and that's why the value is departs from the actual measured value, but it's reasonable as a first approximation. The value of the ripple voltage, and more importantly, it shows from a design point of view what ripple depends on, and basically tells us note that Vm may not be under our control because Vm may depend on the application. So if application requires 6 volts, so this would be 6 volt here. Frequency is also not under our control, is fixed. Frequency is 50 Hertz. Load resistor is also not under our control, maybe, because load may also be defined by application. So the only thing left with you is C here. So by changing C, one can change the amount of ripple that one will get here. So in this case, RLC by T is 5 here. And note that if I increase from 100 microfarad to 500 microfarad here, so according to our expression, C has been increased by a factor of 5, and so therefore it should fall by a factor of 5. And this is indeed what we see here. So it falls to 0.436. Earlier it was close to 2. And our expression gives us 0.48, reasonably close to this particular value here. Okay, and so that's the way to control the ripple, basically the capacitor here. And if you have freedom to choose one, the load resistor also, then one can play around with this also. All right, so let's look at a very quick example. So suppose somebody asks us to design a power supply that will supply 6 volt output to a load of 100 ohms here, 0.1K here, with a ripple voltage less than 0.1 volt. And designing the power supply basically means that we'll have to figure out what kind of a transformer should we use, what kind of a diode we should use, what kind of a capacitor we should use. So let's do that. So for V0 to be 6 volt, the input should be 6.7 roughly. and so the Vs is 311.127 and this is 6.7, so we need a turns ratio of 46.4. So we need to choose a transformer appropriately based on this number here. Capacitor voltage, VR is Vm by F RLC, and that's equal to 0.1 volt here, so that gives us C equal to 12 millifarad here. So we know how to choose it. So 12 millifarad is a particularly large capacitor here, a capacitor of a fairly large size. And so that's one of the price that one has to pay. If you want to reduce the ripple, you'll have to use a large value of capacitor, and that makes the design a little bit bulkier, larger in size. Alright, so the next thing is how do we choose the diode? Because there are a large variety of diodes that are available, and what kind of a diode is suitable for this application. So if we look at a diode, let me show you, for example, these are diodes. There are a wide variety of diodes. So for example, these are diodes meant for rectification, 1N4001 to 1N4007 here. And let's look at the characteristics of this particular diode here. So one of the things that we see here is says surge overload rating of 30 amperes here, and it shows that so there are limits to this particular diode. So it shows that peak repetitive reverse voltage, okay, peak repetitive reverse voltage. So if we choose 1N4001, it can handle only 50 volt. On the other hand, if we choose 1N4007, it can handle 1000 volt here. And then there is the amount of rectified output current that it can handle here typically is 1 ampere. Then there is a non-repetitive peak forward surge current. Okay, peak forward surge current. So forward surge current, it can handle 30 amperes here. And there are others also, specifications here. And so note that the higher the rating, for example, if you choose a 1N4007 with 1000 volt rating here, so that would be more expensive than a diode with a 1N4001 with a 50 volt rating. So we would like to choose a diode which is just appropriate for our application. Unnecessarily, we do not want to choose something which is which has a very high rating, because then we'll be paying a lot more and unnecessarily paying a lot more here. All right, so these are the characteristics. Also note that in this case they're saying that if you have a forward current of 1 ampere here, the diode voltage would be 1 volt. So as we have cautioned you, that 0.7 is just a number that we've been taking for analyzing some of the circuits, and that number may vary depending on the current and the nature of the diode, the nature or the way the diode has been fabricated. All right, so how do we choose a diode for this application? So note that what we require, our choice of diode would be based on how much, for example, average current that is flowing through the diode, what is the peak current. Note that there was a peak value here, peak repetitive reverse voltage, non-repetitive peak forward surge current. So we'll make a choice based on average diode current, peak reverse voltage, peak inverse voltage or peak reverse voltage across the diode, and also the maximum current that may flow through the diode here. So based on those considerations, we'll make a choice of an appropriate diode here. So what we would like to determine is what is the peak current flowing through the diode and what is the average diode current, and what is the peak inverse voltage here. How much is the inverse voltage in the diode here? All right. So this is the diagram that we have been showing here. So the green one is the input voltage here, input at the secondary here, and the red one shows the output voltage here with a little bit of ripple, which is hard to see in this particular case here. And this shows the blue one shows the diode current here. And so the diode current has very interesting waveform. Note that initially what will happen is if I start at t equal to 0 and I switch on my system, the capacitor is uncharged and the voltage here is starts from 0 and starts building up. The diode turns on. The diode turns on. Note that it turns on here, and the capacitor starts charging. and capacitor starts charging, and as the capacitor reaches its final value here, close to this, then by the time the diode current falls to 0 here. The capacitor is fully charged and the diode current falls to 0 here. And then what happens in this region here, we have said that the diode is reverse biased, so therefore the current through the diode is 0. And then because the capacitor discharges a little bit through the RL here, and in the next cycle, once the input exceeds the output voltage here, the diode turns on again and then charges the capacitor. The amount of charge that the capacitor lost through RL is replenished, is restored in this diode turns on here, and then again this part repeats here. So we're not really interested in this particular part, we are interested in steady state part here. So note that the diode is turning on for a very short period of time and basically supplying the charge that has been lost by the capacitor during this period here. Okay, so let's look at it in more detail here. So this is how the red one shows the output voltage here, the green one shows the input, and blue shows the diode current here. Right, so the diode, once it is turning on, so we are not interested in this initial part, we are looking at the steady state part here. So once the diode turns on in this part here, once the diode turns on, the diode is supplying the capacitor, current through the capacitor and current through the load here. Right, so ID, the current that is flowing is C dV0 by dt, that's the capacitor current, plus V0 by RL. Right, so this is the period that we are talking about here. And let's take this period as at this particular part here. Right, so once the output voltage reaches its peak value here, we call that particular point t equal to 0, and this is below. We can choose the origin wherever we want. And so in this region, if we look at V0, so the diode is on, and V0 sort of follows the input voltage here. So V0 is basically Vm cos omega t, because if we neglect the diode drop here for a moment, so V0 is nothing but equal to whatever is the voltage at the secondary. So V0 is Vm cos omega t in this particular region here. Okay, V0 is Vm cos omega t, and because we are talking about a very small region here, very close to the peak, so we can approximate the cos as 1 minus omega t square by 2 here. So we can approximate it by this particular expression here, and therefore we can take this V0, plug it here, and we can then, the derivative is straightforward, and we get this value here, ID equal to minus C Vm omega square into T plus Vm by RL here, because V0 is very close to Vm. If the ripple is small, V0 is approximately equal to Vm here, so Vm by RL here. So that's the diode current here. Right, so our interest is in finding out what is the peak diode current here, this value here, peak diode current, and what is the average value of the diode current here. Okay, so this is what we have here. So we are again looking at here, we said this is t equal to 0, and let's call this part here as t equal to minus delta t here. Okay, just when the diode turns on here, t equal to minus, just when the diode turns on, this is the place where I get a maximum value of ID here. Right, so ID max will be equal to C Vm omega square, and T will be equal to minus delta T here. So that's where minus minus cancels, we get delta T plus Vm by RL here. So our task is to determine what is the value of delta T. How much is this delta T? For how long is the diode turning on here, right? And for that, let's focus on the output voltage here. Output voltage goes like this here, right? So it starts from some VL to some VM here. VL to VM, okay? And then from here, it will discharge again to VL. And then it will rise again to VL to VM here. And so we can use this equation here, right? So we can use this equation to calculate how much is delta T here, because this is the equation, approximate equation, which is valid in this particular region here. It's a cosine curve, but the cosine curve, because close to the peak, can be approximated by this here. So we can put in this value here, VL will be equal to Vm 1 minus omega, and instead of T, we put here delta T here. So 1 minus omega delta T square by 2 here. And from here, we get delta T equal to 1 by omega square root 2 VR by Vm here. So that's the short period of time for which the diode is turning on here. Okay. So now all we need to do is take this delta T and plug it here, and then we'll get what is the maximum diode current here. Okay, so that's what we do. We take this delta T here, we put it here, and we get a maximum value of ID max will be equal to omega C multiplied by square root 2 VR Vm plus Vm by RL. And again, if we plug in the typical values, we'll see that the peak value is here is much higher than the first term here is much larger than VMRL here, and so an approximate value of ID max will be simply equal to the first term here. Okay. The average current is well, if we want to calculate what is the average diode current, so the diode current is flowing like this here. Starts with a high value here, goes to 0 here, then remains 0, then again the diode turns on and it goes like this here. So the average value we can determine as this area under the curve here, half ID max into delta T divided by T here. So we're going to take an average from, let's say, this value to the next peak here, right? So the next peak here, so when you take the average by doing an integral and dividing it by the time period. So the integral is nothing but, if we approximate it by a triangle here, half ID max into delta T divided by capital T. And so we take our expressions for delta T and we calculate and we get ID averages here, ID max here. And we have expression for ID max we've already determined, so we plug it here and we get this final value here. And the final value, if we, as I've been saying, that if you plug in typical values, you'll find that the first term is dominant, and ID average is nothing but equal to Vm by RL here. If you plug in these values, you will find that this is much smaller than the first term here. And it makes sense also that the average current through the diode is equal to Vm by RL, because in a circuit the load RL is drawing a current of Vm, so the voltage, output voltage is approximately equal to Vm, and the average load current is Vm by RL, and that current is what is being supplied by the diode. So the average load current is nothing but the average diode current. So that makes sense. So these are the equations. ID max is omega C square root 2 VR Vm plus Vm by RL. Ripple is over here, and ID average is approximately equal to Vm RL here. And so we can see one trade-off which is there in this power supply design here. Normally we have said that we would like to keep VR small. So if we keep VR small, and to do that, what we'll do is to keep VR small, we'll increase C, right? Now if we increase C here, if we increase C to reduce VR, what will happen is that we're increasing C here, and yes, we are reducing VR, but VR is under square root. So what will end up is that as you try to reduce the ripple, you will increase the peak diode current here. And so let's look at that trade-off in a little bit more detail here. So ID max is omega C here. So what we can do is instead of we can combine these equations that you see here. We can use the expression for VR is given over here, and we can plug in this particular expression here, and C we can take it inside. So we can write ID max is 2 pi in this equation here. And as I've said, this term is going to dominate, and so we can neglect this particular part here. And the ID average is Vm by RL. The average diode current is nothing but average load current here, Vm by RL. And so we can combine ID average and ID max into this equation here. ID max by ID average multiplied by square root VR by Vm equal to 2 square root 2 pi. Now what this equation shows is the right hand side is a constant, and therefore what it is saying is that if you try to reduce the percentage ripple VR by Vm, if you try to reduce VR by Vm, then the first term will increase, which means that the peak diode current will increase. So you'll have to choose a diode which can handle that large value of peak diode current here. And so one can see a trade-off between ripple voltage and peak diode current here, right? So the two of them are related together here, and which is sort of obvious if we see this particular diagram here, because if you reduce the ripple, then the diode, this particular part of the waveform, this particular time period becomes smaller and smaller, and in that small time the diode has to conduct and supply all the charge that the capacitor has lost through RL here, and therefore the peak value will become larger and larger. So as you reduce the ripple, the delta T here becomes smaller and smaller, and therefore I will become larger and larger. So let's see as an example. So we have this 100 microfarad and 1K. Ripple is about 1.95. Average diode current, we said, is nothing but average diode current is average load current, Vm by RL. And we can see the diode waveform here. The diode current about maybe 100 or 200 milliamperes here. Note that the average diode current is 12 milliamperes, but the peak diode current, look at it here, close to 200 milliamperes here. Because the diode has to conduct for a very short period of time, and in that short period of time, it has to basically supply all the load current. Alright, so suppose we increase 100 microfarad to 500 microfarad. So ripple we are going to reduce by a factor of 5, so 0.438. Average diode current remains the same, 12 milliamperes here. And now note the peak diode current here. So peak diode current is almost going to 360 milliamperes here also. Okay, so that's the trade-off that we are talking about. If you try to reduce the ripple, the price that you have to pay is that the peak diode current becomes quite high, and then you have to choose a diode which can handle such a large value of peak diode current. And all right, so the other thing was peak inverse voltage. So the forward voltage is forward. When the diode is forward biased, there is a drop of, let's say, 0.7 or 0.8 volt or so. But we know that in the negative cycle, the diode is reverse biased. But the diode is reverse biased. So let's say, so we have the input voltage here, and using the transformer turns ratio, we have generated a secondary of 12.7. So when it reaches the negative peak here, so the value here will be minus 12.7. The diode is reverse biased, but the output voltage is close to 12, right? Output voltage has a certain small amount of ripple, but close to 12. So the net reverse bias on the voltage here will be equal to 12 minus 12.7, so 24.7. So the peak inverse voltage here, so peak inverse voltage here will be equal to twice of V0 plus about 0.7 here. Twice of V0, 12 here, minus 12 here, so that's 2 V0 plus the diode drop here, 0.7 here. And so note that the amount of reverse bias on the diode will change, will keep on changing, and the maximum amount of reverse bias will occur when this voltage, because on this side the voltage is fixed to 12. So on this side, when the voltage goes to its maximum negative voltage here, which is minus 12.7, that's when the peak inverse voltage on the diode occurs. So that's equal to 2 V0. Right, so we have to choose then a diode with a peak inverse voltage of larger than 24.7 volt here. Okay, so we had seen this designed example, and we had raised this issue of how do we choose a diode for this application. We had found the value of capacitor 12 microfarad here. A transformer we said we should choose with a turns ratio of 46.4 here. And the next task was, how do we choose a diode? Well, so now based on the maximum diode current, we can calculate maximum diode current if we plug in this expression here, so we can get this number. Average diode current is 60 milliamperes here. The output voltage was 6 divided by 10 by 100 ohms, 60 milliamperes here. And the peak inverse voltage is 2 V0 plus 0.7 of 12.7 volt. So these numbers that we have here for peak diode current, average diode current, and peak inverse voltage, these numbers can then help us in choosing a suitable diode for our application. Okay, so let's stop here. We'll continue our discussions and look at a full wave rectifier and also the role of a Zener diode in reducing the ripple voltage.